Well, hello everyone out there. Welcome to part 7 in our energy unit. I hope you kind of noticed we've been building slowly. So in the first couple parts, I described the different forms of energy. And then in the parts after that, talked about how we change back and forth between different forms. And starting in lesson 6, I talked about as those changes happen, what we call transformations in energy. We don't lose the energy, or we don't get new energy. All we're doing is taking the energy that we have, turning it into different forms. So that's an idea known as conservation. We can always identify where the energy is. So if we start with 50,000 joules of energy, we're going to end up with 50,000 joules of energy. So in today's lesson, we're going to look at a particularly common example, and that is a roller coaster. Now, whether or not you're a coaster enthusiast doesn't really matter. I think everybody knows the concept of the roller coaster. So I'm going to teach you some basic ideas about some of the forms of energy, a little more detail than we went into before, and then I'll show you how we apply it to a roller coaster situation. Okay? So we're going to talk about 3 forms of energy that are the most important ones when it comes to roller coasters. I think number 1, the one everybody recognizes, is that gravitational potential energy. When you have a really high hill at the beginning of the ride, that adds a bunch of gravitational potential energy. But the real thrill of the ride is the speed that you get. And speed is associated with kinetic energy. So you're trying to build up as much kinetic energy as you can in these rides. And the other sort of hidden part, the part that's not so good, is thermal energy. Because no matter what type of coaster it is, at some point you've got the track and you've got the little car that you're riding in running on the track. Now, maybe that's, rails, maybe it's little wheels. There's all kinds of different designs, but you always are going to have friction as those things roll across the track. And that friction builds up thermal energy. It would just mean that the temperature of the track and of the wheels and of the rails or whatever, temperature goes up. Now, that's not a good thing. I think coaster designers try to minimize the friction so that you don't have a lot of energy being turned into heat. Because that's not very thrilling to have a warm ride, especially in the middle of summer when most of us go to the amusement park. We're trying to get as much speed as we can. And there's also other factors too. Okay, so let's talk about a couple things that are important to know first. And make sure you write these down. Things to know. Some of this you've heard before. So gravitational potential energy, I'm abbreviating here. We will call that GPE, because I don't want to write out gravitational potential energy every time. So I'll say GPE. Just know that that's what that means. And so here's what you need to know. And I talked about this a little on day 1. It's proportional to height. I'll describe that a little bit more. The amount of gravitational potential energy something has is proportional to its height, which means the higher it goes, the more gravitational potential energy it will have. Okay? So, for example, if something is twice as high, maybe you move it up higher, that means it has twice as much gravitational potential energy. That's what we mean by proportional to. If we're 5 times as high, so let's say you climb up 5 times higher than where you started, you will have 5 times the GPE. Kind of a simple relationship, okay? So we're going to use that when we do some of these roller coaster problems. All right, so that's one thing to know. Number 2, kinetic energy, which I will call KE, is higher when the speed is higher. So I'll ask you that in some of these situations. Remember, you can pause if I start talking too fast. Wherever the kinetic energy is highest is where the speed will be highest. Okay? Typically, you know this, if you ride a roller coaster, your highest speed is at the bottom of the big hill. And there's a reason for that. We'll talk about that when we do one of the examples. And here's the third thing. This is the last thing you really need to know. Friction will build up thermal energy. I'm going to abbreviate that THE. So I'll abbreviate thermal TH, thermal energy. Okay. The more distance traveled, the more thermal energy something will get. That means it'll get warmer. Okay. So roller coasters are warmest at the end of the ride. Okay. Because the entire time they're moving, they're building up this thermal energy because of the rubbing of the parts, the track against the car itself. Okay. So those are some of the important points. Now I'm going to show you how we turn that into what I call a roller coaster problem. All right. Let's take a look. Okay. Here's a typical roller coaster problem as I like to write it. So we've got a real simple drawing of a little roller coaster car, and it's moving along a pretty simple track. We're just getting the basics here. And what I've done is I've shown the roller coaster car at 4 different spots. The starting position at the top of the first hill, and then 3 other positions here at different spots, okay? I've given you some different heights, like the second hill is only 25 meters, whereas the first hill starts out 50 meters high. And I've given you a couple pieces of information. Assuming the car, little car up here, starts from rest. That means it's not pushed, it just is released, okay? Number 2, because friction will cause thermal energy to build up as it moves, I'm going to suppose, and I'm just making this up, that we add 10,000 joules of thermal energy between every lettered point, okay? And what I want you to do is to find all the energy values. So what I'm going to do is I'm going to give you some of the values to start with, okay? So, for example, let's suppose that we start with 100,000 joules of gravitational potential energy and 20,000 joules, because the car, the little roller coaster car, must have some thermal energy. I mean, everything has a little thermal energy. And then your job would be to find the rest of the energies, okay? So it's like a little puzzle, if you will, all right? So remember what I've said, starts from rest, no motion, and we add 10,000 joules of thermal energy every time we get to the next letter, all right? So let me show you the way to kind of solve this. I think I'm going to grab a green pen so you can kind of see what I started with in the black ink and what I'm going to do with the green ink. Okay, here we go. So a couple things you have to remember to do, and this is, in English class, they call it looking for context clues. Let me show you how this sort of translates. Since I said the car is starting from rest, in other words, it has no motion, it's just given a little nudge and then it starts itself down. That means we have no kinetic energy at the beginning, because kinetic energy, as I mentioned on the first page, is related to the speed that you have. So if you have no speed, you have no kinetic energy. Okay, so here's where that's really important. The total energy, and I'm going to encourage you when you're doing a problem to write this down. The total energy is the sum of all the different forms that you have. And I told you we'd only be dealing with these 3, so we don't have to worry about nuclear energy or electromagnetic or anything like that. Sound energy is actually pretty significant in a roller coaster, but we're ignoring that too. So you see, when we add these up, we get a total of 120,000. That's really important to know that, because conservation means we'll always have a total of 120,000 joules, okay? All right, what's the next piece of information to use? Between every lettered point, we're going to add another 10,000 joules of energy. So if we're starting with 20,000 here at position A, by the time we get to the bottom of the hill where position B is, we have another 10,000 joules. So we're up to 30,000 here. And when we get to position C, we're up to 40,000. Again, I'm talking thermal energy now. And by the time we're done part D, we have 50,000. So all I did was I added 10 to each one. Now again, that number I made up. That won't always be true. Okay, here's the other thing to remember. I said on the previous page that your potential energy, gravitational potential energy, is proportional to the height. So if you have no height, you have no gravitational potential energy. Do you notice in positions B and D, there is no height? You're down at the lowest level. So we can write in 0 for that one and for that one. See how we're just putting little pieces together? Now, what about this middle one? I gave you this number on purpose. You see how its height is only half of what we started with? That means its GPE will also be half of what we started with because they are proportional. Not half of the total, half of the GPE. So if we start with 100,000 joules in this height, we're only going to have 50,000 joules, half that much, if we're at half of this height. So I'm going to write 50,000 for that one. Now I've got a lot of information in there. I've never really had to do a whole lot of math either, right? So what's missing? Well, the kinetic energy values are missing, but now we can use conservation of energy to figure out the rest of those. I'm going to zoom in a little bit here. Because the total energy at any of those lettered positions has to be 120,000 joules. So we've got all the numbers here. We're missing one number here, here, and here. But that missing number is the number that makes it add up to 120,000 joules. You can use a calculator if you want to, but I know the number that I add to 30,000 in order to get 120,000 is 90,000 joules. And what do I have here? Well, I've got 50 and another 40, and I need how much more to make 120? That's 30,000 joules. And what do I need down here? Well, at the bottom, I only have 50,000 here, so I need another 70,000 joules to make 120. So that's my last step, is to figure out what I need so that my total is always the same as what I started with. Now, do you notice one thing? If I ask you, where is this little car moving the fastest? The motion is all about kinetic energy. So look at the highest kinetic energy number. As I described to you earlier, if you've ridden roller coasters before, you'll know that this happens usually at the bottom of the first hill, or maybe the biggest hill. So with 90,000 joules, that's the highest we have anywhere, okay? We're going a little slower at the end, but that's because friction has caused some of that wonderful, exciting kinetic energy to be turned into this useless little thing called thermal energy, all right? I guess it's not useless if you want to warm yourself up, but again, I don't really need a roller coaster to warm me up. So that's the idea of how you put all these pieces together to do a roller coaster problem, as I call it, all right? So if you need to play back through this again to see how I put that together, it might be good for you, but otherwise I'm going to turn you loose on your own little roller coaster problem. We'll see how that goes, okay? All right, hope you found that almost as exciting as riding a roller coaster itself. Ha ha.